So, first thing to say is don't pay any attention to the title. Rose is just a student. What I would like to do is to give you a very basic talk, filling in some background on broad swathe of what I consider basic material within the philosophy and foundations of physics. And just as a narrative device, I'm going to frame this within some work I've done over the past couple of months with my collaborator, Brian Roberts. So you always need a narrative. You could read E.M. Forster. I encourage you to ask me lots of questions, stop me asking lots of questions. I'll let you know if the answers aren't things I can complete in a couple of minutes, and then we can move on. But if we're possible, at least it'll help clarify things. It's my intention to try to give you suggestions for background reading, both in terms of textbook material, what I found helpful as a student, but also in terms of the literature, the journal literature, as we go along. So if you have a question about that, pause me and ask me as well. Good? So here's the appraisal of the ostensible narrative. I'm going to begin with the question of what would a geometric conventionalism for quantum theory look like? By geometric conventionalism, I roughly mean the phenomenon that has been widely discussed within the philosophy of physics with regard to space-time, where the same, in some sense, theory can be described equivalently, again in some sense, by either a curved space-time without forces or a flat space-time with forces. So this topic has already come up to some extent in the space-time functionalism part of David's lecture. Eleanor Knox has written a lot about it, but so have many other people, including here James Reed. There's a question about why that sort of phenomenon, the availability of alternative theories depending on the geometry one chooses, the background geometry one chooses, isn't available for quantum theory. So I'm going to raise that first puzzle. I'm then going to move on to a second puzzle about a field called PT-symmetric quantum theory. The P there stands for parity symmetry, and the T there stands for time symmetry. So by parity, I literally mean the thing, the transformation that sends psi of x to psi of minus x. And time symmetry is what you know from your basic quantum mechanics class. It's, in some sense, it's complex conjugation. That's what time symmetry looks like in elementary quantum mechanics. This second puzzle is not about a topic that philosophers tend to talk about, but it has quite a history now in the physics literature. It's a subfield of physics called quantum physics called PT-symmetric quantum theory. And in this subfield, it's often claimed that that theory, PT-symmetric quantum theory, is equivalent to standard quantum theory. So I'm going to claim that these two puzzles are in fact related. It's quite an interesting thing. The first puzzle about geometric conventionalism is something that more or less one can raise just from reading the philosophy literature on space-time functionalism, for instance. It's very natural to bring it over to the quantum case and say, well, what would count as an instance of this phenomenon where two theories can be described by, same theory in some sense can be described by two alternative geometries. The second puzzle is, I think, arrives naturally out of just doing conceptual analysis on what physicists take their own theories to be saying about in relation to standard quantum mechanics. I'll then talk about a much simpler template to explain the second puzzle, and I'll argue that this template is an example of quantum conventionalism. All right. Now the last two sections are a bit more advanced for people with more background. I'll talk about the algebraic perspective to quantum theory and how all this looks from that perspective. And then I'll talk about how this work that we did in fact led to a deeper understanding of observables in a rather different approach to quantum theory, a category-theoretic approach to quantum theory. So let me summarize the trajectory again, okay? So you can think of it as having three parts. The first part, raise an abstract question about this philosophy-inspired thing called geometric conventionalism, and ask how it applies to some new domain within physical theory. It's not just space-time, but also quantum theory. Second part, go find some new puzzle within a subfield of physics that hasn't yet been explored by philosophers. Show that the answer to this puzzle really actually also answers the first puzzle. Third part, feed this back into the practice of mathematical physics and try to see how philosophy can inspire new mathematical physics. So that's the outline. So I've more or less just said this to you in words. So here's some background on geometric conventionalism and geometric quantum theory. Let me say from the outset that, of course, there are all sorts of more intricate philosophical disputes about how to understand what a conventionalist thesis is. I mean to take no part in any of this. Here's the basic phenomenon which we'll be interested in. Geometric conventionalism for spacetime. Now, it's a general fact that in either relativistic or non-relativistic gravity, one can make a conventional choice of either describing the theory by adopting a curved spacetime and representing gravity by means of curvature, or adopting a flat spacetime and representing gravity as what's known as torsion. So if you haven't encountered this term torsion, it's characterized by a geometric quantity. Think of it as force. This latter description, the description where you adopt a flat spacetime and represent gravity in terms of forces or torsion, is often called the teleparallel description of a gravitational theory. Let me do some filling in terms of background. The idea of a teleparallel gravity in something like this sense was first considered by Einstein, although not for this purpose. As I understand it, he wanted to use it as to unify electromagnetism with gravitation. This historical aspect of it isn't a story that's yet been told in detail. Dennis Lemko is working on telling the story, so we'll look forward to that. Now, fast forward to lots of recent philosophy literature. And you'll see that teleparallel gravity in the relativistic case has played quite a large role. So the first recent place where it comes up, I think, is in Eleanor Knox's PhD thesis, and then in an SHP-MP paper that she published, she wrote, I guess she didn't publish, teleparallel gravity, the force of a formulation, so that's the reference. And I think the idea derives from things Harvey Brown said. And so, okay, what does Knox want to do with this? She makes several observations, one of which is the analogy between teleparallel gravity and, the analogy about the relationship between GR and teleparallel gravity on the one hand, and Newton-Cartan theory, this curved theory of Newtonian gravitation, and standard Newtonian gravity on the other hand. So I think that's one of the really fruitful observations that she makes. It's an analogy in Knox's paper, and she then, connects it to space-time functionalism, which I won't talk about, but we can raise that again in Q&A. It's an analogy, and then there's a more precise version of the analogy that's given by James Reed in his B-Phil thesis. So there's that Reed. And there's a recent preprint by Reed and me showing that actually if you take this teleparallel prescription and you literally apply it to Newton-Cotton theory, it spits out Newtonian gravity in the standard sense. And we also show, which I won't go into right now, that it's consistent with the relativistic description of such phenomena. The point is that there is a well-defined mathematical machine. Call it the teleparallel box. If you have a curved theory of gravitation, in the usual sense, it doesn't matter if it's Newton-Cotton theory or GR. You take it and you drop it into your teleparallel box, and it's going to spit out for you some kind of flat-spaced description with forces or torsion. Yes?
Just in terms of references, is the teleparallel stuff related to, I think Feynman in his lectures talks about formulating GR and like a spin-2 field on a Minkowski space?
Good.
But I don't
Good.
know if that's the same thing as...
No, it's not the same thing. Yeah. Feynman is taking a particle physics point of view to describing gravitons. That is I think of that as much more related actually to the string theory description of trying to start with your space-time target space, your wall sheet being embedded in the space-time target space, and then computing what now dynamically what you would take the metric to be, starting from that perturbative field theory. Right? So that's the spirit of the Feynman proposal.
And so just to contrast, in relation to that, how would you characterize the spirit of this?
This is supposed to be a theory which is, in some sense of equivalence, really demonstrably equivalent to GR. So I'm going to say exactly what sense that is, right? So for instance, in Feynman's proposal, you're not going to start with that and literally show that the space of solutions is the same. Maybe you could, but that's not something Feynman showed. Yes. Yeah, and there's, in terms of quantization, it's not like this would be more perturbative than GR. It has the same status. It would be a different quantization, as you'll see, because the Lagrangian is different. But it would be equally perturbative or equally non-perturbative. Whereas the string theory Feynman strategy is essentially perturbative, until you find a way to fix it. Did I answer your question? Yes.
You say this one approach is, these two approaches are geometrical, and the other, the final approach is not.
Yes. Absolutely. Yes. Yeah. Okay, so what is this thing called the teleparallel box? The way the machine works is you start by redescribing GR in a certain formalism. So just as in electromagnetism, you have a gauge field that's valued in U1. Right. So that's this thing you call A for this standard electromagnetism course. You have this gauge potential called A. Right. So it works the same way here. You try to write down similar kinds of fields for GR. You write down gauge potentials. The difference is that there's two. One gauge field is going to be valued in the Lorentz group. And the other gauge field is going to be valued in the translation group. Now you put these two things together, and of course you get the full Poincare group, which is the group of symmetries of Minkowski space, the Lorentz group plus translations. And the way you get, so, okay, that's a starting point. From the starting point, you can either get GR, or you can get the teleparallel description. The way you get the teleparallel description is you take this gauge field for the Lorentz group, and instead of letting it have a field strength, you say the field strength vanishes. What this effectively does in your space-time theory is it sets the curvature of space-time to 0. And now you've got to do something else because you just eliminated a whole bunch of degrees of freedom. So what you do is you absorb those degrees of freedom into the translational part. And this manifests itself as, in the space-time theory, as something like a force. So here's the sense in which this ends up being equivalent to GR. You can write down a Lagrangian for the theory. That Lagrangian is equivalent to the Einstein-Hilbert Lagrangian up to a boundary term. So it's not actually equivalent. Up to a boundary term. One can then show that at the level of equations of motion, the two theories end up being the same. So at the level of solutions, they end up being the same. So as I said, this machine can be run for both the relativistic and the non-relativistic case. In the non-relativistic case, you do need some secret sauce to make it work. And that's what James and I did. What does that mean?
Could I just ask, so how do you interpret the spin connection?
Yes, the spin connection tells you about inertial degrees of freedom. It doesn't capture anything but a choice of inertial frame and how things look from the choice of inertial frame.
So does this teleparallel gravity work only with, okay, so I'll give an example. Let's say I wanted to put a direct wave packet in GR and to do with teleparallel gravity. Normally what I would do is you need to couple the spinor bundle of the direct wave packet to GR using the spin connection.
Yes.
And it's unclear to me if you set the spin connection to 0 how you do this.
Excellent. So note that I have not set the spin connection equal to 0. I've set the curvature of the spin connection equal to 0. This is a very perceptive question. In fact, there's a long history of discussions of whether teleparallel gravity is consistent or inconsistent, precisely due to the kinds of considerations that you're raising in broad outline. Let me draw people in a little bit. So there's all kinds of ways in which one might try to individuate a physical theory. In this particular case, say a field theory. Right? We might say it's the same theory if it gives rise to the same equations of motion, thus has the same solutions, in the sense that it has the same models. Here's a more demanding sense of equivalence. It not only has to do what I just said, but it has to behave in the same way with regard to how you couple it to other theories. This modal sense is much more demanding. There's been some discussion of this in the philosophy of literature. I think a little bit of it has already come up in Dave's talks, actually. This is some kind of lying in the background, some of these things, supersymmetry. One place where, idea of understanding a theory as being embedded within a network of theories comes up in Gordon Bellot's Understanding Electromagnetism. That's one of the great morals of that paper. Right. So, anyway, I'm just trying to show you that this question that, what's your name? Aaron, is it falls under the genus of a question that's already live within the philosophical literature of theory individuation. So yes, the coupling is not supposed to, answer quickly your question, is not supposed to be an issue for this version of teleparallel gravity. There's another version where I literally set the spin connection to 0, and then I have trouble coupling to spinorial matter. Okay? So here's a picture for you, just of the left-hand side is the curve description, if you like, call it the GR description, Newton-Cartan description, where a free particle follows a geodesic. In that same motion, you can convert it into the teleparallel picture where it's flat and there's a force or torsion that enters into the equation of motion for the particle. So here's the first puzzle. Can one do the same thing for quantum theory? I'm going to raise two prima facie problems, which I don't really think are problems at all, but that's what you might immediately think of when you ask this question. The first problem was that the line of thought that leads to space-time conventionalism proceeds by appealing to different space-time connections. Different, if you like, let me just, in an accurate way, let me say, different ways of differentiating.
Nick,
Yes.
so you don't mean quantum gravity here, right? You mean
No,
something
I
like
just mean
non-relativistic quantum
vanilla.
mechanics.
Yeah, vanilla quantum mechanics. Yeah. But quantum mechanics is not a geometric theory. Right? So how do you get the structure to emerge? Because I think once you see the way the teleparallel machine, something a teleparallel machine works, it's natural to think that, yeah, anytime you can put theory in geometrical form, you can do something like this. Then depending on how one interprets the theory, one may or may not get a connection to some doctrine about functionalism. So I'm not claiming that in the quantum case we get a connection to some doctrine about functionalism. That's an open question. Does everyone understand problem one? So problem two is that quantum theory doesn't have forces in its usual description, right, which is based on Hamiltonian formulation. So how would one get an analog of this kind of space-time conventionalism? One description has the forces. That's what you use to absorb the degrees of freedom that the geometry carries. This is a response to problem one that ultimately also leads to response to problem two. There is, in fact, a natural way of viewing quantum mechanics as giving you something close to what we think of as geometry. So remember, Hilbert space has an inner product. Complex inner product. Now this inner product can always be decomposed into a real symmetric part and an imaginary anti-symmetric part. One can interpret this real symmetric part as a Riemannian metric, and one can interpret the anti-symmetric part as a symplectic form. So at this point, I'm going to give you a bit more of a background talk. You look at the way, sorry, this is very coarse grade, so it's not quite, it's accurate up to first order. The two dominant subfields within the contemporary study of geometry are, on the one hand, Riemannian or Lorentzian geometry, right? So that's a smooth manifold where every point you put the tangent space with a Lorentzian metric or a Riemannian metric. And then the entire thing has curvature. You can study all kinds of things about these objects, right? And on the other hand, there's this other kind of geometry which was inspired, which came out of Hamilton's principle in mechanics. It came out of doing mechanics within the Hamiltonian framework. And this approach to geometry is, this kind of geometry is called symplectic geometry. It's a very, very large subfield by now. And the idea in this kind of geometry is that the way this kind of geometry is defined is you start with a smooth manifold, but at every point, when you look at the tangent space, in fact, you can do it for a small neighborhood in this case, that local geometry doesn't now have a metric that measures distances. It has a different kind of structure that measures oriented angles. So I'll give you an example in the two-dimensional case. Let's just say R2 equipped with a structure that measures the oriented area within, so this area along with, between two vectors, along with a choice of direction, that's the oriented area, is an example of a symplectic geometry. Now, you can study things that are vastly more complicated than this. Another example is the sphere S2. That's also equipped with a structure that measures oriented area. That is going to be an example of a symplectic geometry. Now, the reason this was studied so much after Hamilton discovered his version of Hamiltonian mechanics is because it turns out that instead of writing down Hamilton's equations, which you remember, this is, you write down the time derivative of P, momentum, as round h over round q, where round is Hamiltonian, and q dot as minus round h over round p. Right? You pick up the minus sign is a convention, where you put the minus sign. Right, instead of doing that, we're actually writing down equations of motion. What you can do is you can absorb that structure of the equations of motion into the intrinsic geometry of these kinds of manifolds. Just in the same way that instead of writing down Newton's equations of gravitation, you could absorb that into geodesics on a manifold with a curved connection. So what I'm trying to show you, without going into too many details, is that at some level of generality, you can see that the same kind of game is going on. The interesting thing is that on this natural way of geometrizing quantum mechanics, what you get has both structures, and they have to play together nicely. So I won't say exactly what it means to play together nicely, but they play together nicely in the sense that they are related by a complex structure. Right? So here's the upshot. An n-dimensional Hilbert space, whereby by n I always mean complex dimensions, can be equivalently described by a 2n-dimensional real linear space with a symplectic form, a complex structure, and a prescription to use that symplectic form and complex structure to define a Riemannian metric, a ruler. Right?
So
Yes.
the Riemannian metric is a positive defined metric.
Yes, positive definite. Yeah. And in this case, it really is just a Euclidean.
Alright, just
In this case, yeah. Now, as you all know from your basic quantum mechanics course, when you describe quantum mechanics in terms of a Hilbert space, that the global phase of that particular subsystem, you're only studying that subsystem, doesn't carry any physical information. You can always change everything by a global phase. And as you also know, you can quotient out by that global phase. So if I'm studying, for instance, here's a study question for you. So if I'm studying the two-level quantum system, so my Hilbert space is C2, and I quotient out by the global phase, what do I get? Faculty are allowed to answer.
you'll get something like a bank, right?
So it's a space of rays, right? What is the space of rays? In this case. Yeah, it's a block sphere, right? It's just that the S2, right? And S2 has a metric, and that metric actually just it's a Riemannian metric. S2 also has the symplectic form that I mentioned to you, and that is an example of the kind of thing I'm talking about. So even when you quotient out to the actual space of states without redundancy in a sense, you get exactly the kind of geometric structure that I'm describing to you. Okay. Now, Hey, don't look here. Yeah. I was just telling you about how symplectic geometry emerged organically out of Hamilton's approach to mechanics. Right? Just doing mechanics of Hamilton's equations. What happens when you geometrize the picture in terms of symplectic geometry is that you can say, let your Hamiltonian just be some smooth function on this space. So some smooth function. And from any of these two functions, I can always take the first derivative. And this symplectic form, this structure, it has the form of a non-degenerate 2-index tensor, and I can always now hit the derivative with this to get a vector field. The point I want to emphasize is that this vector field, when you look at the integral curves, the flow, you flow along the vector field, those will precisely be the solutions of Hamilton's equations. So what you're saying is that for this kind of geometry, just take any smooth function, and that could act as a Hamiltonian, or an observable in principle, generating Hamiltonian dynamics along the curves along the vector field.
What is this omega?
It's a symplectic form. Yeah, it's a non-degenerate anti-symmetric closed two form.
We assume you have that structure already.
Yes, we're assuming it's given. Okay, so right, the interesting observation when you geometrize quantum mechanics is that you can play exactly the same game. You can describe what your standard unitary evolution as the Hamiltonian flow of a certain Schrödinger vector field, which is in turn the Hamiltonian vector field of a certain class of functions that are compatible with the metric. The Riemannian metric now encodes expectation values. So remember, think about the block sphere. The antipodal states are going to be exactly the orthogonal states, according to your inner product. The symplectic form encodes dynamics, and there's been some discussion here in the philosophical literature about how to apply these things to quantum mechanics. So there's a discussion about no cloning, comparing classical and quantum theory. And there's also a discussion of time reversal by Brian Roberts, the philosophy of science paper. Again, comparing the classical and the quantum case. Now, more background. There's also a broader debate about what one ought to take the geometry of mechanics to be, and the ontological significance of that geometry. So two references here are a paper by Jill North, where she defends, this is in Journal of Philosophy, but I'm forgetting the title. Can someone help me with the title? Structure of physics, yes. She defends the Hamiltonian point of view of mechanics, Hamiltonian geometry, exactly the symplectic geometry I'm talking about, as the more conspicuous way in which to understand mechanics. And there's a paper by Eric Curiel, where he defends the Lagrangian approach to mechanics, in particular the geometric form of the Lagrangian approach, as the more conspicuous way of understanding mechanics. So really a debate about geometry, actually. Yes. It's kind of question here that those of you who know the foundations of quantum mechanics literature will immediately ask, which is, what about, okay, you've given a geometric model for Hilbert space. What about the algebraic foundations of that sort of model? I mean, in particular, the following. It's long been known that you can start with a C-star algebra of operators, quantities, and reconstruct a Hilbert space in which these are represented. So you have to assume that there's a state and a few other things. So this is known as the Gelfand-Marx-Segal theorem. It can be summarized as, once I give you the C-star algebra and a state, you know everything. You know all the models. Since quantum theory can describe geometrically as a combination of a Riemannian inner product and the symplectic form, surely there ought to be an analogous theorem for writing algebraic foundations for these geometric models. So Brian and I have shown that you can start with a slightly different, but very closely related algebraic structure and obtain quantum theory as representations of these guys on a Kähler manifold.
Sorry, can you repeat the last thing you said? You can start, can you say when you said?
Yes, you can start with a distinct but related algebraic structure and construct the geometric models as, sorry, let me back up. In the standard case, you can construct Hilbert spaces as models of an algebraic structure, and not just Hilbert spaces, operators on them as well. Hilbert spaces and bounded linear operators as models of this C-star algebraic structure. So now that I've given you a geometric model for describing a Hilbert space, it's natural to ask, what could you have a similar kind of algebraic foundation? And the quick answer is you can, with some caveats.
I know. Is a Jordan-Lee-Banach algebra is it related to just a Jordan algebra?
Sure, it's a special case of a Jordan algebra.
Okay. I've seen kind of reconstructions of quantum mechanics in terms of sort of Jordan. I mean, I guess that's why Jordan made the Jordan algebras in the first place, right?
Yes, so there's a long history here. So, this thing called a Jordan algebra is it is commutative, but non-associative. That's one of the key properties. So, and one can see in a lowbrow way, if you think about the matrix product, you can always have, the symmetrized and the anti-symmetrized part. What the Jordan product tries to do is to model the symmetrized part. Jordan, and to some extent, I guess, von Neumann, got interested in this algebra because they thought it ought to be possible to give the product of two quantities, two things you think of quantities, an operational meaning, in the sense that if you take the product of two quantities, you should get another quantity. As we all know, this is not true of, for instance, standard matrix product and quantities in quantum mechanics. You can take two self-adjoint things, take the product of them, and end up with something that's non-self-adjoint. What Jordan wanted was an algebra where something satisfies the condition for being observable. You take two of these things and you multiply them in a relevant sense, and you get another observable. Right? So this is the origin of the Jordan product. It's true that there are various reconstructions that involve the Jordan product. That's because the Jordan product is related to the triple slit property. So if you know what that is, but let me not go down that rabbit hole. Okay, so but now we're in a position to give a responsive problem 2. Right? Problem 2 was that, look, how are you going to draw this analogy when there are no forces in quantum theory? And I think the answer, one should just say that one doesn't need forces in order to give an analogous geometric conventionalism description. The kind of conventionalism that will be at issue here is always going to be relative to the kind of geometry one's dealing with. So what one would, and we know that we have a symplectic geometry, a Hamiltonian geometry. So what one would instead expect is that something like the following phenomenon. Given a Hamiltonian or symplectic geometric description of a theory, a conventional redescription should proceed by introducing an equally valid but different symplectic structure and some kind of compensating term to describe the Hamiltonian flow in one geometry as a non-Hamiltonian flow in the other geometry, right? Because in this other geometry, there would be a compensating term. So it's a bit like the force thing, except you can always introduce a compensating term.
So,
Yes.
Sorry, I'm asking this as a clarificatory question because I feel like it might be helpful to others too. Is the geometry that you are trying to, you and Brian are trying to be conventionalists about, is it the geometry of Hilbert space or the geometry of the space that the quantum field theory is set on, or the quantum theory that is set on?
It's the geometry of the Hilbert space.
Geometry, yeah. That's what I thought. But I was just like,
Yes. Thank you. That's important.
Yeah.
It's the geometry of the Hilbert space, or this alternate description of the Hilbert space.
Yeah.
So in a way, so this is the template for what we seek. At this stage, we've identified a puzzle about why there is no geometric conventionalism for quantum theory. We've cleared some of the obstacles to thinking that some form of geometric conventionalism is impossible. But we don't really know what precise form such alternative theories might take. And it seemed really hard once we thought of this to just try to constrain, how do you go look for such a thing, right? Just try to write things down. Well, it turned out that there was a better approach, which is to go look for a different kind of puzzle, where people claim that there is an alternative description of quantum theory. So that's what we're going to right now. It turns out that one precise form will come from thinking about a prima facie different puzzle. PT-symmetry, heterodox observables, and a puzzle about equivalence. So here's a seemingly different puzzle. Well, this is just background. There exists an intriguing subfield of quantum physics called PT-symmetric quantum mechanics that was initiated by these two physicists, Bender and Bottker, in 1998. This is by now a huge subfield. This original paper has 1,000 citations. It's inspired techniques that people have used a lot in quantum information theory and quantum optics especially. So quantum optics community really got on board with some of these ideas. What Bender and Bottker do essentially is they relax the self-adjointness of observables to the requirement of PT-symmetry. At the stage, let me remind you of something. The standard characterization in textbook quantum mechanics of what an observable is, what a measurable quantity is that an operator, a bounded linear operator, that algebraically is self-adjoint. So when I say algebraically, I mean I don't want to fuss with domains and codomains. Okay. So if you know what that means, that's for you. If you don't know what it means, ignore it. But algebraically, the important thing is that if I take in matrix form the complex conjugate transpose of a matrix that represents an operator, I get the same thing back again. A dagger equals to A, or A star equals to A is how people sometimes express it, where the dagger or star, what it does to matrices is complex conjugate transpose. So everyone remember this from your elementary quantum theory? That's just part of the structure of standard quantum theory. Now, these physicists say that we should relax the self-adjointness observables to the requirement of a certain kind of symmetry, PT-symmetry. And furthermore, they claim that when this PT-symmetry is exact, which I'll mention more about, this new kind of quantum theory is actually equivalent to ordinary quantum theory. They also claim to provide an important generalization in the inexact case. What does such equivalence amount to? That's the new puzzle. Now, it's not clear that this has anything to do with our previous question about how to construct equivalent theories with different geometries, but generally, non-trivial equivalences are rare. Right? You don't just come upon these things, as opposed to field redefinition. So it's at least worth investigating.
So, Nick, a quick question. So the reason why we should think that PT symmetry is related to the conjugate is because we assume CPT symmetry of the theory in general, or?
No, we're not assuming anything about CPT right now. Because we're doing quantum mechanics.
Yeah.
There's no CPT theory. This is something that's introduced by hand by these physicists as a surrogate for what they consider to be the stricter condition that observables have to be defined algebraically as self-adjoint. Okay? Now, there is a natural connection to complex conjugation in the sense that time reversal symmetry in standard quantum mechanics involves complex conjugation. So let me give you, before getting into this, I want to give you some context for this topic of PT symmetry from the more general perspective of thinking through heterodox observables. Anything that's not just self-adjoint in quantum theory. There exists a tripartite classification for quantum observables. This was introduced by Brian Roberts in his paper on real observables. The three properties that one can assign to operators, they can be symmetric, normal, and have a real spectrum. I'm not going to talk about symmetric, because here we're only interested in normal and real spectrum. What normal means is an operator is normal if A dagger equals to A dagger A. So clearly, being self-adjoint is a special case of being normal. What real spectrum means is that the eigenvalues are real. Now you might want to challenge, by the way, that physical quantities should be set up, and physics should be set up in such a way that the eigenvalues, the results of experiments, the eigenvalues, are real. Why not use complex numbers? Right? Just assign just use them to represent different things. Instead of use I and minus I to represent what we usually represent as 1 and minus 1 in a spin experiment. Brian goes in that direction. So that's a territory that's covered in this Unreal Observables paper, which I highly recommend. Very, very nice and very accessible. Nice drawings too. Always. For us, we're not going to challenge that. What I want to emphasize to you is that any two of these properties, when conjoined, imply self-adjoint. So the only way to relax yourself out of a self-adjointness requirement is to drop one of these properties. Okay? And like I said, I want to focus on this case where the conjunction of normal and real spectrum implies self-adjoint. It turns out to be surprisingly hard to find real and non-self-adjoint operators that are in some sense adequate for representing quantities. What I mean by adequate representing quantities, I mean that your prescription for probabilities has to work out, has to be empirically adequate. I mean that your prescription for these quantities generating the dynamics, the unitary evolution, also has to be adequate. Right. So that's quite a strong bunch of constraints. The tale of PT symmetry can be understood as a tale about trying to gain control of this regime, the regime in which you might find real and non-self-adjoint operators that are in some sense adequate for representing quantities. That's the game these physicists are playing. Sorry, why is it not? Oh, here we go. Sorry, this is just an illustration of the tripartite classification, where any two imply self-adjoint. And I'm trying to show you, actually, that we're not going to be interested in this entire region here. It's just some small part. Questions?
When you say it's very hard to find these things to represent quantity, do you mean because maybe if you add those two things together, you get something that doesn't look like a quantity, or is because, or why is it hard to find
Yes, because how do you know you're going to have a consistent probability rule?
Okay.
Number one, how do you know it's going to generate unitary dynamics? Number two, I mean, the magic words here are Stone von Neumann theorem, right? That's the thing that's as far as dynamics, that's the thing that's really pushing back against you. So I don't want to go into the more technical thing, and probably David has better knowledge of that particular aspect.
Not than you, I think.
Than me, but Alex.
Yeah, I was just wondering, is the reason that we wouldn't want to go to non-normal, like we wouldn't get a spectral decomposition or something?
Good.
Like that?
Yes, exactly.
Okay. Yeah, it doesn't seem necessarily super motivated, just that expression, unless
Yes.
you already assume it's something.
Great. Thanks for that. Yes. So the importance of an operator being normal, I'll just finish this and I'll come back to you, is that you have a well-defined generalized spectral decomposition. So what that's something that's pushing back against you in that other direction. So actually, what I'm going to do, or what these physicists have done, I'm going to show you, operates in like this really thin space where they don't run afoul, actually, of the perceived problems of not being normal, and they don't run afoul of the Sturm-von-Neumann theorem. So you'll see why in just a moment. But it's a very, very small space. Sorry, in the back. Did you have a question?
I just didn't hear what was said.
Now, I've only been talking about individual quantities. Often, when dealing with physical theory, we're interested in some collection of quantities, not just one quantity. And as you know from the structure of quantum mechanics, again, the textbook version, there are really strong constraints, often mentioned, under mentioned under the heading of compatibility of observables, on when you can have a suitable set of operators taken together that provide you with a good set of observables. Right? So this led Brian to, in this same paper on real observables, he defines an adequacy condition on sets of observables called sharpness. So Brian says a sharp set, S, is a set of operators such that if the if is very important, if A equals to BC, for some A, B, C in this set of operators S, then BC equals to CB. Right? They commute. Because if they didn't commute, then suddenly you would have as one of your observables one of the things that precisely could not be measured by the lights of the commutation relations of some subset of the other observables in your set. Let me give you a concrete example. Take the Pauli matrices that you all know. So I should say that in this entire talk I'm going to assume that you've had standard undergraduate first course in quantum mechanics. So the Pauli matrices are your standard observables for a two-level system. Right? And the sigma x, the sigma y, the sigma z, and we know that. So now, that's actually the set of things we usually take as a collection of observables that we like. Now, we also know that sigma x and sigma y don't commute. And let's make sure you're listening. What's sigma x times sigma y? Good. Sigma x times sigma y is I sigma z. Now suppose that if instead of our set sigma x, sigma y, sigma z, we have sigma x, sigma y, I sigma z. That's an example of something that violates this condition of sharpness. Because the third thing, I sigma z, is equivalent to sigma x, sigma y, and sigma x, sigma y don't commute. So it's not internally consistent. Okay, now we're ready to go back to understanding what these physicists have done in the PT-symmetry program. To quote from Bender and Buckner, they've discovered a huge and remarkable class of non-Hermitian Hamiltonians whose energy levels are real and positive. In the more sophisticated examples, they're generally using they're working in infinite dimensional systems, Schrodinger representation, where the P symmetry sends C of x to C of minus x. The T symmetry sends C of x, the wave function, to a complex conjugate of C of x, right? And here's what's meant by it being a symmetry. It's a standard definition that David already gave. It means that the P and T operators commute with an operator. So P and T are symmetry of that operator. I wrote H for Hamiltonian, if P and T commute with that operator. Now, nothing I'm going to say depends on having one thing you pick out as Hamiltonian. You just write in H. And furthermore, symmetry is called exact, just in case the eigenvectors of the operator are invariant under the symmetry. So this is the background setup for their examples. And here's one really, looks simple, but it's really non-trivial. This is what they call the PT-symmetric.
Nick, don't walk quite. You're coming off the camera if you walk too far forward.
Sorry. What we need is really projective space. So I can just, never mind. So notice that if this epsilon term is 0, this is just a harmonic oscillator, right? Yes? We both have some factors. Anyway, this is just a harmonic oscillator. And when it's just a harmonic oscillator, then the Hamiltonian is clearly self-adjoint. Yes? But the minute I introduce this extra ix term, and I let e be greater than 0, a real number greater than 0, I spoil the self-adjointness. Homework problem. Compute the spectrum of this thing. So this was what led Bender and Buckner to think that, there might be some room for maneuvering within the space of non-self-adjoint things that you can still control, non-adjoint, but you can still have a real spectrum. They did a lot of numerical simulations, and it turned out that it looked like the spectrum was real. The actual proof that the spectrum of this thing is real involved techniques from integrability and all kinds of sophisticated things, right? So that proof was given maybe 6-7 years later. Okay, so this means, look, that there's some work for philosophers here, I think. This is a reference to Gershwin. The advocates of PT-symmetry claim that it extends standard quantum theory, and they give, the kinds of examples I just gave you. And so in particular, some subpart of PT-symmetric quantum theory must be equivalent to standard quantum theory. Now, philosophers can try to clarify what exactly this equivalence consists of. It turns out that this provides one kind of answer to our abstract question about geometric conventionalism for quantum theory. This is not supposed to be clear to you at this point. Here's a simplifying assumption we'll use. We'll only deal with a finite dimensional template for PT-symmetric systems, because now we can really have control. And here's our finite dimensional template. Again, I'll only assume that you've had a standard quantum mechanics course. Consider now for a finite dimensional system with so in particular, a finite, an operator, a bounded linear operator on finite dimensional Hilbert space with non-degenerate complex eigenvalues. Okay, that's the kind of object I want you to consider. I've called it H. Now, any such operator can be decomposed into a real part and an imaginary part. The real part I've called A, the imaginary part I've called B. The real part is self-adjoint, A self-adjoint, and B is self-adjoint. So for this generic complex operator, I can study its eigenvectors. Yes? And there I've written the eigenvectors of H as C. Now notice that I'm not making the assumption, which is often made in textbooks, that you should have an orthonormal basis of eigenvectors. No, I'm just studying eigenvectors in general. Yes? I'm now going to alert you to consequence of this fact.
So what does finite dimensional mean in that? That's the dimension of the Hilbert space,
yes,
or the number of eigenstates? No, it's the former.
I mean, since this is has a non-degenerate spectra, if the dimension is, I'm dealing with finite dimensional Hilbert space, then I'll have a complete basis of eigenvectors.
Right, but it'll have more eigenvectors than dimensions, because they're not orthonormal, right? So
no, not necessarily, because I can then construct, for any such system, I can construct the minimal complete set of eigenvectors. And they don't have to be orthonormal. They just have to be linearly independent.
So the example I have in mind then is coherent states and the annihilation operator, and so they're all eigenstates of the annihilator. It's not finite dimensional.
It's not finite dimensional. Yeah.
But I'm wondering, there's like...
Yeah, so we can talk with infinite dimensional case and how to do it
But
later on. Yeah, but
won't in general be the case that it has more? I mean, it has more eigenstates
you
than the dimension of the Hilbert
you can
space.
always construct more if you want, right? But what I'm saying is that I can, in these cases, I can always have the minimal complete set.
Okay, so but the finite dimensional is counting the dimension of the Hilbert space
Yes.
and not the number of the eigenstates.
Yes.
Yeah. Okay.
But sorry. So, but the minimal complete set will turn out to be
Sure, of course.
yeah.
That's what's minimal about it,
Yes.
right? Yeah.
Good. Yes. So the thing that the important point I want to emphasize to you is that now when I look, because H is not self-adjoint, this top equation and this bottom equation are truly distinct. I can study separately the eigenvectors of H dagger and the eigenvectors of H. Yes. If H were self-adjoint, then that would just be the same thing. And so I can also study the way H acts on the duals. So that's here. You just pick out that eigenvalue, which is the complex conjugate of that eigenvalue. Do the same thing for both sides. Okay. Everyone good with that? I'll stress again that these are not in general orthonormal. With that in mind, so remember psi is the eigenvectors of H and phi is the eigenvectors of H dagger. One can always construct something like an orthonormal basis, but not an orthonormal basis. It's what people in literature call a biorthonormal basis. You can choose the sequence psi phi to be normalized in the following sense. Yes? And then you can have something like projectors and something like a completeness relation. Although, of course, they're not actually projectors or a completeness relation. You can sum this series, and it equals the identity, where n is the dimension of the Hilbert space. And each one of those things functions exactly like a projector. So when you take 2, you get the identity back again.
You mean you get the same?
You get the same one, sorry.
Yeah.
Yes, yeah, sorry.
Each one of what things?
Each term in the completeness relation functions like a projector. But, sorry, well, again, the reason it's not an honest projector, the reason these are not honest completeness relations, the reason it's not an honest orthonormality in the usual sense, is that you're not taking phi orthonormalized with the dual of phi. You're taking phi orthonormalized with the dual of the eigenvector of the complex conjugate transpose of the operator. Yes, the key to seeing how all this works out is that psi and phi are eigenvectors of 2 different operators. And one is H and one is H dagger. And now H can be, now you have a surrogate spectral decomposition. Yes, H can be expressed like this. And this is called the biorthonormal spectral representation. So good. Nothing I've said so far implies the spectrum is real.
Yeah. So what about H adjoint? Do you just flip sine phi in that spectral decomposition?
Yes, that's right. And you have to take the complex conjugate of the...
Oh, yeah.
Yes. Yes.
In this case, H is PT-symmetric.
I haven't said anything about PT-symmetry yet. Yes, I'm just defining objects. Right? So I'm just defining objects. I haven't said anything
I
about
just didn't know if I'd missed.
Sorry?
I just didn't know if I'd missed something.
Oh, no, you didn't miss anything. I'm just setting up machinery. When is the spectrum real? So H, here's the theorem. H has real spectrum I mean, given everything we've assumed, I mean, the theorem is not proving for infinite dimensional cases. So. But there should be no problem with non-degenerate spectrum. H has a real spectrum if and only if H is pseudo-Hermitian, which I'm not going to define. This is a theorem proved by Mostafazadeh. And H is pseudo-Hermitian if, just in case, this algebraic condition is satisfied, where H dagger equals to eta H eta inverse, where eta equals to sum O dagger O, where O is an invertible linear operator. In particular, this means that eta is self-adjoint. Let me help you understand this condition. It's clear that this is a generalization of what it means to be self-adjoint. And it's clear that it's not just a generalization, it's a kind of symmetry-related weakening. What you're saying is that it's self-adjoint up to a similarity transformation. Whereas the thing that's doing the similarity transformation is your eta. Yes, it's some self-adjoint operator. So now we know how to, given these assumptions, we know how to ensure that the operator has a real spectrum. Of course, you know, self-adjointness is a trivial case of this. I just repeat again. Now, what if we're dealing with more than one operator? We want a set of operators. If we're dealing with a collection of operators, then a natural condition to introduce is that of being simultaneously pseudo-Hermitian. That means that for your collection of operators, you can show that they're pseudo-Hermitian using the same eta. There exists an eta such that you can show that each of these operators is pseudo-Hermitian. As opposed to, for every such operator, there exists an eta. Now, something that Brian shows, it's a cute one-line exercise in his Unreal Observables paper, is that any set of self-adjoint operators is sharp. It satisfies the consistency condition that we mentioned earlier. It's a few more lines of algebra to see that any set of simultaneously pseudo-Hermitian operators is sharp. So now you found like a non-trivial way to extend the domain of what can count as sharp. It's a good sign that this respects a natural constraint that you would impose on a set of observables. Okay, here's where we're really going to get into the physical interpretation of this pseudo-Hermitian condition. I've given you a condition to ensure that given some particular kind of assumptions on your operator, namely that you have a bi-orthonormal basis, you can have a necessary and sufficient condition for the spectrum being real. That's what I call the pseudo-Hermitian condition. What's the significance of this? Well, from just the previous explanation of pseudo-Hermitian condition, you might think the significance is if you're a believer that the eigenvalues have got to be real to represent the results of measurements, then that checks that box. Right? But there are deeper reasons. Let me go to the second bullet point first, because the first bullet point is more complicated. The second bullet point is where I think things will really start to get clear. H is pseudo-Hermitian, just in case H is Hermitian with respect to some new inner product, defined like this. So what does this mean? It means that being pseudo-Hermitian is a hair's breadth away from being Hermitian. It means I can always, okay, I'll back up. Remember that being Hermitian in Hilbert space formalism is always defined with respect to a particular choice of inner product. And what we do in standard quantum mechanics is we just fix the inner product of Hilbert space. And then we say, this is Hermitian, that's not Hermitian. But we didn't have to do that. And actually, it's precisely being serious about not doing that that opens up the way to this kind of quantum conventionalism. one could say, hey, I'm going to choose a pseudo-Hermitian operator, and actually everything's going to work out fine as long as I choose the right inner product. Clearly, it can no longer be the inner product with respect to which this operator is pseudo-Hermitian. But I could have chosen some other thing. Right? And it turns out that the property of being pseudo-Hermitian is exactly equivalent to being Hermitian with respect to some new inner product. So it's so close, conceptually, right? The first bullet point is also revealing. We're running out of time. This is revealing. It says that H is pseudo-Hermitian if and only if there exists an anti-linear involution such that that involution is a symmetry of H, and that involution preserves the eigenvectors of H. Okay, these are just words. These are just words. I want to tell you what these words mean. So, you probably recall from your first course in complex numbers or something, why you had to define the complex plane this way that, remember wondering, why is it that this direction has to be I, and this direction has to be the real line? Right? Of course, there was no necessity about that. That was a choice of coordinates for the complex plane. And one way of talking about where the real line is that doesn't make a choice of coordinates is to say, hey, there's this transformation on the complex plane that if you do it twice, it comes back to the same thing. And there is a set that's invariant under this transformation. That's the real line. That's a way of doing it that doesn't appeal to coordinates. So in the elementary case of the usual choice of coordinates for the complex plane, what you're doing is just you're reflecting the top half to the bottom half, right? And the thing that's left invariant is precisely what we conventionally call the real line, the complex plane. Now it's clear that if you had chosen a different kind of symmetry, you could have picked out something else as the real part. Yes? This condition is essentially telling you that for operators, that first condition. It's trying to give you an invariant way of picking out what's going to count as the real subspace in your space of operators. This sets stage for simple conventionalism. The characterization of which operators count as quantum observables can't be done independently of a probability rule coming from a choice of inner product. For instance, one can choose between Selfadjoint corresponding to the standard inner product, or one can choose pseudo-Hermitian corresponding to some eta-deformed inner product. So, sorry, we're now in a position to come back and answer these questions that some people had about how do you avoid the problems of normal, how do you avoid the problems with, what's the other thing? Oh, yes, yeah, unitary evolution, right? Not getting unitary evolution. And the answer is simple. You avoid it by choosing the right inner product. That's what this conventionalism amounts to. So it's obvious from this that you always get unitary evolution. You always get the normal spectral decomposition as long as you choose the right inner product. Right? The thing that I think was missed for quite a long time. See, let me say something in front of an analogy here. This is essentially the whole problem. Right? The whole argument. It's just for quantum mechanics. And in space-time, people didn't have the tendency to fix a particular metric. People who worked after a certain point, which was pretty early on in the history of GR, everyone just used an isomorphism class of Riemannian manifolds. But for whatever reason in quantum mechanics, and certainly in the textbook tradition, in the quantum information theory tradition, we've always tended to, when working on those bases, fix a particular inner product. And you don't have to. So I'm not yet, okay, I'm eventually going to say what the equivalence amounts to, but Now I want to first give you a really concrete and visceral example of what's going on here. You remember the Pauli matrices from your studies of two-level quantum systems, right? I'm going to recall for you some of these properties of the Pauli matrices. The Pauli matrices are a representation of a certain algebra called SU2. This just means that they have all the algebraic relations that the algebra has. If you add the identity matrix to the Pauli matrices and you take the real span of these objects, what you get is a real vector space of self-adjoint matrices. So by the way, this is an example of Jordan-Lieb algebra. You don't take the real span. You could take the complex span, use complex coefficients, and then you would get the complex vector space of 2 by 2 complex matrices. Note that this is actually a Hilbert space using the Hilbert-Schmidt inner product. The space of 2 by 2 complex matrices is itself a Hilbert space. And I witness the matrix formed in the Pauli matrices. They're conventionally written. So here's an example that Brian and I like to use. It's the main example in our paper, actually. These, following Dorkey-Brody, we call these the deformed Pauli matrices. Now, sigma 2, big sigma 2 is just the same as small sigma 1. Sigma 1 and sigma 3 are different. So, small exercise for you. Sigma 1 and sigma 3 are obviously non-normal, right? Just because of the way we've taken linear combinations of small sigma 1 and small sigma 3. They're not normal. It's easy to convince yourself that, well, actually, let me not make that comment. So lambda is a parameter here, beta is a parameter. Lambda has to be a real number, lambda squared has to be less than 1, and beta is that expression in terms of lambda. So why does one set these kinds of constraints on the parameters? It's because we're trying to find real eigenvalues. So if you didn't have constraints, there's no guarantee you end up with real eigenvalues. So just trying to solve an eigenvalue problem, find real eigenvalues. Claim. It's easy to check that this is also a representation of SU2. It also provides an orthonormal basis in Hilbert-Schmidt norm. Sigma 1 and sigma 3 are manifestly non-self-adjoint. Indeed, they're not even normal. But these are pseudo-Hermitian. Indeed, they are simultaneously pseudo-Hermitian. That using the same eta, I can take a sigma dagger and show that it equals to eta sigma eta inverse. And so I can choose a bi-orthonormal basis, which is actually just the eigenvectors, as you can see, the orthonormal basis is the eigenvectors of sigma 3. I can choose this orthonormal basis, bi-orthonormal basis, and I can write now sigma 1, sigma 2, and sigma 3 in this bi-orthonormal basis. Oh, surprise. Actually, it looks, now they have exactly the same matrix form that small sigma 1, small sigma 2, small sigma 3 usually do in the 0, 1, or plus minus basis. And one can also write eta explicitly, thus showing that explicitly constructing the inner product with respect to all these things are self-adjoint. A different choice of inner product. And furthermore, in this discrete system, okay, now we're going to talk about PT-symmetry. One can easily define a parity operator, a complex conjugation antilinear operator, time reversal, and thus arrive at PT-symmetry. And one can show that the existence of PT-symmetry is related precisely to this existence of an antilinear involution, which is one of the defining conditions of being pseudo-Hermitian. It all comes together. So the PT-symmetry is not the main thing here. It's what these physicists use to get at this phenomenon. But it's really this phenomenon of the conventionalism of choosing, being able to say Hermitian with this inner product or pseudo-Hermitian with a different choice of inner product. that is at the heart of this phenomenon. That's when you get the space where you have real eigenvalues, non-normal according to one inner product, and yet you get to say everything you always want to say about quantum mechanics. So now this is a bit more sophisticated, an algebraic perspective of this phenomenon. The cleanest way to say what this equivalence consists in is by appealing to the algebraic approach to quantum theory, where you do things in terms of C-cell algebras and Jordan-Liebknecht algebras, and then you can directly use the Gelfand-Naimark-Segal theorem to construct the Hilbert space and represent operators acting in Hilbert space. So notice that clearly the Paulis they generate a Jordan-Liebknecht algebra, and you take a complexification of that, you get the C-star algebra, and so do the deformed Paulis. What is the relationship between these two C-star algebras? Obviously, they're not identical. Okay. So what is the relationship? Recall, a C-star algebra is an associative algebra that is turned into a Banach space by a choice of norm. And the next level structure is that it's equipped with this involution, the star, satisfying certain properties. There's only one property that I want to point out right now. I want you to attend to this property called the C-star property, which the C-star property tells you how the star interacts with the norm of the algebra. One thing you can see immediately is that the Paulis and the deformed Paulis, they must have a different star. By the way, sorry, I'm switching notations. Star is just complex conjugate transpose. It's just dagger in the matrix formulation. They must have different stars because according to one star, an operator is Selfadjoint. According to the other star, it's not. So these two algebras clearly have different stars. Now, the reason I ask you to attend to the C-star identity is because it's a really strong statement. What one can show is that given a particular norm, it fixes a unique star. So they must also have different norms. Now we're in a position to really get to what these physicists are saying when they say our version of quantum theory, this PT-symmetric thing, is equivalent to standard quantum theory. What they've done is they've constructed an isomorphism between two C-star algebras with the same underlying associative algebra, but a different norm and thus a different star. And by the way, there's no guarantee that you could construct such an isomorphism in general, right? That's why this is non-trivial. And the way they arrived at this was by using PT-symmetry. But in finite dimensions, one can just do it directly, it turns out. So that's the answer to the puzzle about equivalence. It's also, I claim, an analog. There may be others, but the kind of analog of the geometric conventionalism one sees in space-time theories. Like any analogy, there are things that are not the same. For instance, in the space-time case, the curve description, it generally works this way. The curve description can be, you can start with the curve description and reproduce a whole bunch of flat models related by symmetries. Okay. It's a question of how to individuate models, but let me just talk about this. With regard to what I've said so far, there isn't an analog of that one-to-many, or in the reverse direction, many-to-one phenomenon. One could try to set things up so there's an analogy of this kind. If one said that the analog of the curved space-time description is actually the reduced Hilbert space. It's, in the case of two-level system, it's the sphere. And then one could imagine moving from the sphere to different Hilbert space descriptions. So that would be one way of trying to draw a closer analogy. It's also not clear that there's anything like inertial frames going on here. So the way you move from the curved space to the non-curved space description in the space-time case is that you take a tetrad and then you fix a gauge by imposing constraints on this tetrad. it's not clear that there's any kind of Dietrichson thing going on here, or what it's not clear what would be the analog of a tetrad, right? So these are all questions for future research, future investigation.
Nick, so that didn't occur to me when you sort of set things up before, but if you think back to sort of origins of conventionality and
Yes.
Poincaré, it's not a space-time conventionalism, it's just a space conventionalism.
Yes, exactly.
So why, so it sounds like from what you're saying, but you are trying to look for an analog. So the objection, you know, the lacunae that you just sort of identified don't seem to be there if you look for an analogy to space conventionality
Actually,
rather than space-time.
This is really worth discussing at length. I'm not sure that they wouldn't be there. So, so for instance, here's one way of thinking. I mean, one problem is that the actual example Poincaré uses, the temperature thing, doesn't really have dynamics. You know, it's a very kinematic example.
Yeah. Well, that was kind of what I was kind of getting at, I guess.
Yes, but and this example does have dynamics, incidentally. It's just a different form. It's already in Hamiltonian form, but it does have dynamics. The other thing one can say is, if suppose you could imagine introducing kind of geometric conventionalism for particle mechanics, where you treat a particle as a field theory, right? Dynamics of particles as a field theory from a world line into some target space. It doesn't have to be space-time. It could just be a target space. And then you add some, you say, I want it to move on geodesics. Right, that's the equation of motion. And now you ask yourself how to redescribe this in terms of flat space. It doesn't seem to be an obstacle to doing this, and it seems that, I mean, again, it would have to be investigated in detail, but if you introduce certain kinds of symmetries, you might even get a one-to-many correspondence. Right, if you had, yeah, the right sort of structure there. Sorry, right.
So just a quick clarificatory question. Are the two theories that are supposed to be equivalent, does the unconventional one say the only observables are the Selfadjoint operators, where Selfadjoint is relative to the star sub 2?
Yes.
So what about, my initial reaction was like, there's a third theory which says the observables are either Selfadjoint or, pseudo.
More general formation.
Yes.
Yeah.
Yeah. So you can always say that, like, it's whatever is an invariant under the symmetry, right? So I'm only going to talk about Hilbert spaces up to isomorphism. Right. Okay. Then you would get one theory back again. Right. In that case. Okay. Yes.
Okay. I'm
Yes.
just glad.
Yes. And but it's true that is in a way, saying that is very generic. The interesting about his literature is that someone was able to come up with an interesting kind of isomorphism, where the things where you obtain precise control over how the spectra of, the heterodox things looked from the perspective of the orthodox kinematics. Does that make sense?
I mean, sorry to interrupt, but we
Yes, we
already
need to
in
go.
lunchtime,
We need to go. So I was going to talk about category theory, but I think we should go to lunch. Yeah, great. Thanks very much.